Perfect. So this is we used to say artist's impression. This is an AI system's impression of what would happen if a black hole evaporated past extremality. I'll define all this in a minute. But for most of the history where people have been thinking about this, the reaction has sort of been like, uh-oh, we don't know quite how to handle that. Um, And it's not totally clear whether this will actually happen, which is why the title is a question mark. But if it does happen, I'm going to make a claim, which let's say the claim is remarkable, which is that what happens is the black hole's gone and the matter comes back out. So hear me out. Hopefully, I built up enough credibility as a card-carrying general relativist to study black holes my whole career. This is actually not so crazy, and in fact, it's quite natural. The part that many people might still consider crazy is that these two frames, that you would actually have this process. But let me get into all of that with my next AI-generated art. Don't worry, the whole talk won't be this, but I did have a good bit of fun at the beginning. So I love studying black holes because they're so incredibly simple. You know, if anyone's married, you know how hard it is to pick anything out, right? If you want to buy like a chair, there's so many options for chairs. You could get the giant yellow ones that fit two people. You could get the little ones that, there's more than three numbers to pick out a chair. If you were going to order a black hole, you really only have to pick three things: the mass, the spin, and the charge, which is pretty remarkable. There's nothing macroscopic like that. What makes black holes unique. These are real rigorous results for stationary black holes. This is it, and they're all described. You got the full metric and Maxwell field in the Kerr-Newman solution. This is sometimes called the no-hair theorem. I think of that as a name. I wouldn't make too much of what hair is or anything. Point is, there's three numbers. Now, if this were an astrophysics talk, I would immediately cross out the charge, because in the astrophysical universe, there's lots of plasma hanging around that would neutralize a black hole that built up a charge. But since this is a theory talk, instead I'm going to cross out the angular momentum. That makes my life much, much easier because everything is going to be spherically symmetric. So maybe the second most important fact after establishing the parameters themselves is the range of the parameters for which you really have a black hole. So I've set the angular momentum to 0. I just have the charge of the black hole Q and the mass of the black hole. And part of the whole theory of black holes is that you can't have too much charge in your black hole. You can write down an exact solution that has charge Q greater than mass M. But it won't have an event horizon, won't have this surface of no escape. It won't be a black hole. So a black hole can't have too much charge. And then the special case where the charge equals the mass, the boundary between black hole and no black hole in parameter space, that's called extremal. So that's just the technical term, and my whole talk is going to be about that limit. So with that very basic introduction, this is a good point to pause and just say, I really want questions. I didn't know exactly what level to pitch this talk at. I might have gone way too low. I might have gone too high given people's backgrounds, but the underlying problem is very simple. I think I could explain everything to any one of you individually, one-on-one in an hour. I could tell you everything in this paper, but getting the group dynamics right, I'll rely on your questions. So please, whenever you have a question about anything related or tangential, just speak up. Okay, so maybe the biggest breakthrough about black holes after realizing they were a thing that could actually form, of course, was Hawking radiation. So this cartoon here really has withstood the test of time. It's a good cartoon for the origin of Hawking radiation, that you sort of imagine there are particles and antiparticles in the vacuum. And if you had an event horizon, what could certainly happen theoretically is that one particle might fall in and then the other particle would escape, and that particle would be seen as radiation emerging from the black hole. And then the ingoing particle is kind of just as important. That has to go in with negative energy, at least as energy is defined at infinity, to balance the positive energy that's escaping, and that has to back react and reduce the mass of the black hole and maybe its charge and angular momentum if that particle carried those numbers as well. So that's the cartoon. I think it's a pretty good cartoon, but of course the calculation is where the money is. And the temperature of the Hawking radiation, famously the spectrum is thermal, and the temperature is given for the spherical black hole with no angular momentum by this formula up here. And I want to have everyone used to thinking about the fact that there's two special radii, R plus minus, call them the outer and the inner horizons. The outer one is the event horizon, the inner one we'll get to. It's actually very important to this story. So if you've always ignored the inner one when seeing this before, you're in for a treat today. And this, as long as we're away from, in the limit of black holes, these, those are real numbers because Q is less than F. Now there's two limits where the temperature is very low, and both are going to play a role in this story. So first of all, if you make the black hole really, really big, you can see from the R plus squared in the denominator in the scaling with n that the temperature is going to fall off like 1 over n. So a large black hole has a very low temperature. That's going to be important. You can also get a low temperature for a finite-sized black hole by approaching the extremal limit. So remember, when these two are equal, that's an extremal black hole. And then you see we have one minus the other up here. And so you're approaching 0 temperature in the extremal limit. So those are two kinds of low temperature black holes. Now, the big observation about large black holes, which is not my observation, it goes back a long time. This is the last AI picture. It's getting a little wonky here, but we'll run with it. Is that if you have a large black hole, sufficiently large black hole, remember its temperature is getting smaller and smaller the larger it is. So eventually that temperature will get smaller than the mass of the electron. And then it's not going to emit electrons. It's going to be exponentially suppressed. There's going to be actually no way for a very large black hole to discharge. It's basically emitting photons and gravitons. So you want to think about that energetically. It sort of doesn't have enough energy to break up an electron-positron pair out of the vacuum and turn it into Hawking radiation. So that means that large black holes naturally, if they have charge, naturally evolve to this extremal limit. So this is not going to happen in astrophysics, but as a theoretical physics problem, it's very clean and very interesting. You start with a sufficiently large, sufficiently charged spherical black hole, and it's not going to discharge. It's going to lose mass due to all that photon and graviton radiation. It's not going to lose charge, so its charge is going to decrease and decrease until you get to its mass is going to decrease and decrease until you get to the extremal limit where the temperature is 0. So you start with that very large black hole. It's going to tend towards this extremal limit. And then you might ask, well, how extremal? So this really started with the paper from 1991, where the authors pointed out that, it'll eventually get so low that just one of these quanta emitted with this thermal spectrum, characteristic temperature KT, just one of these quanta would be enough naively, if it actually were emitted, to take you not just to extremality, but over it, right? Once you get to if you solve, using the formulas on the previous page, for when the Hawking temperature is equal to how much your mass is larger than your charge, how much sort of energy you have available to emit while being above the extremal limit, you'll find this number. And at that number, you might worry that something very strange is happening. The authors up there concluded that something goes wrong with Hawking's calculation, that the semi-classical approximations he made break down. In this talk, I'm going to accept this. I'm going to say, suppose the emission really does happen. And then you kind of wonder, well, what happens next? It was sort of clear that when you were a black hole and you were emitting quanta and they were carrying away mass, that you just had a lighter black hole. But now what happens if you somehow jump over the extremal limit? Okay, so as I said, these original authors and the prevailing view since 1991 was that this won't happen. Something must be going wrong with Hawking's calculation. The idea is maybe this doesn't feel right to be thinking of a thermal spectrum where one photon would change the temperature by a substantial fraction of the temperature, for example. That's one kind of argument advanced. And there have been a lot of arguments and a lot of work on this that I only learned about recently. As I started thinking about this whole topic just a few months ago. But Pear's paper from earlier this year is one reason I wanted to come to UCLA to learn more about that. So I will just say there are a lot of arguments on this side. Based on my very limited perusal, I have not been totally convinced, but I want to learn more. And if I wanted to point at one sort of issue in these arguments that I would want to understand better, there's a certain near horizon limit that's always taken to make things simple. It's not totally clear to me how that interacts with the full asymptotically flat picture. But I'm really not in a position to refute this. I just think it's worth considering what seems very natural to me, which is that really the assumptions of the Hawking calculation ought to be fine. I don't really see anything going wrong with it. It's a sort of remarkable statement that, a thermal distribution is kind of a statement about you're sort of maximally ignorant of the system, and black holes are, nothing comes out of them, so you're maximally ignorant, and it comes out thermal, and, there's a prediction that this happens, and I'm going to just take that prediction seriously from the point of view of this talk, that there really is going to be a last quantum emitted. And at that point, what you thought was an event horizon really isn't. In the GR lingo, we have various kinds of horizons. We could call it an apparent horizon. We don't need the precise definition of that. And what I found, as I said, is that in this case, what's going to happen is actually the matter is going to come back out of the black hole. So yeah, perfect.
Do you care about the asymptotics? Are we in asymptotically flat? Or yes.
Thanks for the clarification. Everything I did is in asymptotically flat, but certainly for a small black hole, there won't be much difference. For a large black hole, maybe there's some reason there's a difference, but I haven't thought about it. One of the things I'll ask at the very end is just, is this interesting to repeat this story for ADS? What might we learn from that? From that change. Anything else? I was going to ask for questions anyway. Okay. So just briefly, what did Hawking do in a little more technical detail? There's really not a lot of assumptions. So a big one is that he's going to fix the classical background space-time and do small perturbations. So of course, he's really working with, a scalar field or something, but people have in mind the linearized system, with graviton and photon fluctuations. And then you have to say what state you're in, and that's not totally obvious. Hawking did it by starting from collapse. An important contribution to Unruh was clarifying what's going on at late time and how that's universal. None of this is controversial, just to list the assumptions. And then what you get out of it is really a lot. So famously, the spectrum in terms of, number density or expected number of particles is thermal, but it's more than that. It's really the whole density matrix. It's just identical to black body radiation if you also include the fact that the thing emitting it has a non-trivial space-time between it and you. These are sometimes called gray body factors for people who studied this. But the point is really that you can compute everything very explicitly. And in this explicit computation is the prediction that these particles would be emitted. And I personally haven't seen anything special about low temperature within this calculation. Now, other arguments, there are other claims being made, but at least within Hawking, it looks fine. And there was some concern in the 90s, I think, that the stress energy tensor might be blowing up on the horizon, that got cleared up. The stress energy tensor is fine. So there doesn't really seem to be anything internal
to Hawking. What about the first bullet point? Does the space-time change a lot if you emit that last quantum?
That's my next slide. No, not locally. The global causal structure is quite different, but locally it's a tiny change.
But that is the one point where this other perspective would say that's the assumption that fails. That
the fixed classical space.
Well, the free quantum field that you can't. It's not really free.
Yeah.
That's the point of contention.
Okay, so the first one is being targeted. Yeah, I have the bias that if it's a small amount of energy, it should have a small change in the space-time, but we should definitely want to learn more about that. I will say there's also a loophole that, nobody has actually done this calculation for the coupled photon-graviton perturbations, which is really, and I think, you correct me if I'm wrong, I think the claim is that these bigger effects are only there for gravitons, right? You wouldn't see it in a pure scalar.
You would, if the pure scalar is coupling to graviton.
If it's coupled, yes, but if it's decoupled, I think you don't see it at all, right?
Right.
So if something's going to go wrong within Hawking, we're going to have to redo it with the coupled
Yeah.
scale, which you started to do in your paper. I don't know if anyone else has done that.
Yeah.
Looks really interesting. Anything else? Okay, so here's my assertion that it's a tiny change. That's just an assertion. But this is what it looks like to me with my pre-existing shots and on the subject. So it's a tiny amount of energy, tiny effect on the space-time. And so the mental picture I'm advancing is that, it was this AI thing was kind of nice because AI really knows what's been written down, right? And AI totally picked up on the fact that in the literature, there's a lot of kind of fear of like, this would be a huge thing, it's like red and jagged. And I want to argue that it's not. It's a tiny difference. So instead of thinking of it as like a super different thing, I would replace this with, it started out, it was just barely a black hole. When we got down to this last quantum, it's within a hair's breadth of being a black hole in parameter space. The parameters changed due to this discrete event, and now it's, still just barely, not a black hole, but a very similar. So that was my thinking when I started thinking about this, which was actually a few months ago. And but then, of course, if you're allowing this to happen, you have to ask, if it's not a black hole, what is it? And so this is where some of the new calculations will come in. And basically, you got to go back to what formed this black hole if you're going to have any hope of answering this question. So you have to study the matter that was going to follow. So that's what I did. This is the paper. We just assume that this emission does occur, and then we ask what's left behind. And so, just the very simplest thing. They're combining pre-existing ideas that have been done in slightly different contexts. So the classic model of gravitational collapse uses a thin shell of matter. It's just analytically solvable with an exact GR, so that's great. And the key point here is to also include somehow the back reaction due to the Hawking radiation, the thing that is reducing the mass of the black hole. And that's done with something called Weij's space-time, which is basically just promoting the mass parameter in the black hole space-time to a time-dependent thing in a natural way. Gives you a stress energy tensor, which is null and has this funny name, null dust, but has been used for a long time to model this kind of back reaction. Yeah.
So do you really have to assume this emission, or can you compute the probability for this emission from?
Yes, you compute the probability based on those assumptions from the previous slide.
It's not zero.
No. There's clear prediction of these assumptions that the probability is non-zero. It will happen if these assumptions are correct.
But you basically assuming that all of these assumptions.
I am, yes. Yeah.
And let me just say, if you really say a free quantum field, then by definition it doesn't back react, so it didn't actually change the mass.
Fair enough. Fair enough. I'm also assuming the back reaction is done in the obvious way, where whatever energy of that quantum went out is just subtracted from the energy of the space-time while preserving spherical symmetry. I guess strictly speaking, that's an assumption. It feels like almost the same thing as this, but fair enough. I'm not self-consistently doing back reaction within quantum physics. That's important to say. In fact, you pointed me to your thesis, and it looks like you started doing that. You have a shell in there and everything. And you're saying something else. It's I want to do this.
Zero. I think there's zero probability for this.
No, I know. I know. Yeah. Paris disagrees with all of this. But I didn't realize you had constructed the self-consistent back reaction with the shell, I think, which is exactly what I want. Okay. All right. So for the remainder, I'll go through the paper. I'm going to start by, well, it's review, but probably you haven't thought about it since I hadn't really studied it until I started working on this problem. And this work should be more famous than it is. But going back to De La Cruz in Israel and Bowler in the late 60s, early 70s, there were papers on just collapse of charged matter using this thin shell model. So it's a beautifully simple analytic model. You just say space-time is flat inside the shell. What is it outside? Well, if you assume spherical symmetry, you have a theorem that tells you the exterior space-time is described by the same metric as a static black hole. So you get to use the so-called Reisner-Nordstrom metric outside. You just glue Reisner-Nordstrom to flat space-time in a radius that you allow to vary in time. There's a well-defined way to define the distributional, delta function stress tensor of this shell, and you just assume it has no pressure. Simplest thing. And what you find is that the equations for the motion of the shell, which are just a simple consequence of general relativity, although it's really just the energy conservation part of general relativity. The consequence is that the equation involves three parameters: the total charge Q, the total mass M, so that includes, gravitational mass. And then there's this other thing, little m, which I sometimes call mass of the shell, I sometimes call it energy. That's a little hard to say exactly what it is, except that it appears in the stress energy tensor of the shell, in the sort of time component, proper time component of the shell. But you can't distinguish between rest mass and internal energy or any of these other things. Fluid people would talk about. It's just the mass is associated with the matter. All right, so here's Reisner-Nordstrom. Now, you're maybe more used to this if you've seen it in terms of a coordinate little t, but probably you at some point, learned that you should change coordinates to cover the event horizon if you're interested in the event horizon. And so these are the Eddington-Finkelstein coordinates. Then I'm going to use exclusively, there'll be no little t at all. That's going to be very useful later when we do the back reaction. But I want to emphasize that, even though I have this written in the form with little v that is sort of associated with going to the horizon, this could be a super extremal spacetime with no horizon. And in fact, it's only regarded as the exterior outside the shell. So if the shell is bigger than this horizon radius r plus, this spacetime doesn't describe the radius r plus. It's not. So Reisner-Nordstrom, don't think of it as a black hole. Think of it as the spherically symmetric exterior to a massive charged body. So just to be clear, it's always this v coordinate. The interpretation of v is it's constant on ingoing null rays. So that's just when I say time, I'm going to mean v for the rest of the talk. And this radius is the usual one, which is related to the area of a two-sphere. And we won't need any of the rest of Reisner-Nordstrom. So if you studied this before, there's a whole intricate structure of fully extended Reisner-Nordstrom with other universes. And, we don't need any of that. We just need the region covered by this, because that'll be sufficient for describing gravitational collapse. Okay, how many people here love Penrose diagrams? All right, some half-hearted Penrose. So I'm not going to make too much of it. On the other hand, it's really hard to explain what's going on if I don't have a diagram. So the rule here of this kind of diagram is that light goes at 45 degrees, just like in special relativity. So you see the causal structure immediately from this Penrose diagram, and it's spherical symmetry, so every point is representing a two-sphere. So to think about what can happen in gravitational collapse, what we want to do is look at this Penrose diagram for Reisner-Nordstrom and imagine sort of drawing shell trajectories on it. So to the right of the shell trajectory is going to be Reisner-Nordstrom, and the left is going to be flat. Now, as we do that, we want to keep in mind how big the shell is. So can be quite confusing if you've never studied this before, but I've given you some key shell sizes, okay? So these lines over here, future null infinity, that's where light rays go. If you shine a flashlight, it ends up here. Past null infinity is where light rays come from. So these are arbitrarily large radius. So if the shell is ever here or at this point, it's gotten back to infinity. Okay. And then going to the left, this event horizon here has size r plus. This thing I'm calling the inner horizon has size r minus. This thing I'm calling the Cauchy horizon also has size r minus. So all of this has the same radial size. And then the only thing that's actually small is this singularity. So for example, one thing a shell could do is the shell could come in from the past. So it's a time-like shell. So everything that is moving at less than the speed of light on these diagrams originates from this point back here. So you could imagine the shell coming in, reaching a minimum radius, and coming back out. So I'm going to use the phrase bounce. If a shell does this, this would be failure to form a black hole. So if we solve the equations for the radius of the shell as a function of time and found it did this, we'd say no black hole forms. And then the diagram we draw is we cover up everything to the left. So we erase that. Okay, so this is the situation. We could find this in principle for a parameter regime. You'd be described by Reisner-Nordstrom outside of your bouncing world line and flat space-time inside. This describes failure to form a black hole. Someone want to jump in and ask me something to clarify Penrose stuff, or should I just plow through this? This is the simplest. Okay. So here's something else that could happen. We could draw this trajectory. We'd have a shell that would go in like this, cross R0, so now our horizon is forming, and just end up at this purple line. I'll explain later why that's called Cauchy horizon and so on. For now, it's just a purple line. And so in this case, a black hole really does form. But the important thing to notice, which is going to be a theme, is that the matter did not reach the singularity. It never collapsed to zero size. So this picture of a shell of matter collapsing to zero size, this is a very special thing to no charge, no angular momentum. I think it's totally non-generic. I think it basically doesn't happen. And I don't know why so much effort is devoted to studying it. I think this is much more like the generic case. The matter ends up at a finite size when it hits this thing. We'll talk about what happens next. But it stays at a finite size equal to this r minus. So it's the size of the inner horizon defined by its mass and charge. So for this case, we would again cover up the back, and this would be what the Penrose diagram looks like. You have the event horizon, and you have this Cauchy horizon.
Are all these black holes then equivalent, no matter where it's in? Can you from the outside tell like at what radius?
Not from the outside, but if the matter comes back out, which is what I'm going to say happens, then you will be able to tell the difference. Now, there was an interesting paper by Gary Horowitz and some other folks. They did this bouncing shell in ADS. They did a null bouncing shell. Same thing happens if it's null. Just looks like this. I'll show a diagram later. And I think they argued that the boundary correlator has some sign of whether it bounced or not. So maybe quantum mechanically, duality-wise, there is, but classically, no, you can't see what happens inside the event horizon. Okay, this might be a good moment to discuss the Cauchy horizon, since now we have a shell reaching it. So Cauchy horizon has a technical definition involving the domain of dependence of initial data, but actually the thing I'm calling the Cauchy horizon isn't a Cauchy horizon in the technical sense. Everybody does it, so we're just gonna imagine Cauchy horizon is just the term for this purple thing, okay? What's going on at the Cauchy horizon is something Roger Penrose pointed out a long time ago, which is like the most mind-bending factoid you can, torture your general relativity students with. And you can see it from this diagram. So the way this Penrose diagram works is you brought infinity to a finite location. So a light ray shined like this, traveling forever, reaches this point. So the whole history of the outside universe is happening. Whatever's going on out here, it's happening. Okay. Everything that ever happens occurs up here. Right? But when it sends in, if you imagine sending in signals, or you just perturb the space-time, you're here, and perturbations propagate out causally, you see this Cauchy horizon can be reached in finite proper time by the shell. How many people have heard of this before? Just 1, 2, 3. Okay, this is so cool. Penrose said this a long time ago, right? So you can reach, an observer could reach this Cauchy horizon in finite proper time, but the whole history of the internal universe to the end of time is also coming in. So this observer, if this were an observer, not necessarily a shell, that observer, she would see everything that happens. It would be super compressed, it would happen in finite time, and it would be highly blue shifted because of it. So this is the famous among relativists anyway, blue shift instability of the Cauchy horizon. So this is in part why you don't see this diagram so much. People aren't totally sure what actually happens outside of spherical symmetry, but there's been a lot of progress on the mathematical side, showing that actually with classical physics, not much happens to the Cauchy horizon. You go beyond spherical symmetry, include perturbations. It's actually been proven it stays a very weakly singular thing. Everything is finite, basically, that an observer would see. So let's leave that for the moment as a mystery, because I'm going to come back to the Cauchy horizon. I'll let you digest it. But and from the classical physics, you just sort of say, I'm not sure what happens at that. Okay, so you could also, bounce a little further in. Qualitatively, this is basically indistinguishable. Doesn't really matter. I'll just cover up. Looks like that. So now you see a piece of this so-called inner horizon. Qualitatively, it's the same. You form the black hole with the Cauchy horizon. And the other thing that could happen in principle is you can hit the singularity. There is a tiny, highly contrived parameter space for this within spherical collapse. But I think that's an artifact of spherical collapse. I think it'll disappear the second you go outside of that approximation. So I'm not going to worry about this one too much today. Okay. Any questions about this diagram before we proceed?
Mm-hmm. To understand, very simple question from drawing, light trajectory particle, or are you drawing in time?
This is time-like, so light always goes at 45 degrees. So the event horizon, for example,
why there is an event horizon?
The event horizon is just a property of the Reisner-Nordstrom spacetime.
Your video is Reisner-Nordstrom.
Yes, but it's not an extra assumption. What I'm going to assume is spherical symmetry, and then there's a theorem that tells me that the unique spherically symmetric metric in Einstein-Maxwell theory is Reisner-Nordstrom. I don't have to assume static. So even though the shell is dynamic, its exterior is exactly Reisner-Nordstrom, much like in classical electromagnetism. If you had a shell of charge Q, because charge is conserved, the field outside is exactly Coulomb. So this is the analog of that.
Sure. I thought you want to construct a black hole by drawing the
Yes, I mean I do. That's why I picked the initial conditions for the shell, such that it will collapse. But the way you prove that a black hole follows from collapse is you assume that spacetime is flat inside of the shell, in the shell model. And outside, you just say, I'm going to solve Einstein-Maxwell equations. But then you immediately conclude it must be Reisner-Nordstrom. And then you solve for the trajectory of the shell. And if it gets small enough, then you see the part of Reisner-Nordstrom, which is a black hole.
Right, but if the outside of the whatever shell is flat, then why do you have event horizon?
The inside is flat. The outside is Reisner-Nordstrom. It's I have spatial pictures of it later. Let's revisit it when I have spatial pictures. Yeah.
If you go inside the inner horizon, does it always have to hit the singularity, or can it hit the Cauchy?
No, in fact, it usually hits the Cauchy horizon. This is the generic picture. I believe I'm working on showing it. I believe you will never hit the singularity outside of spherical symmetry. I think it's an artifact of spherical symmetry. In any case, even within spherical symmetry, to hit the singularity, you have to do weird things like build the shell with so strongly gravitationally bound that it starts at inside its own horizon. There's weird things. It's very hard to make it hit the singularity. I'm arguing this is generic.
And does this happen also in finite time, or?
Yes, according to the shell's clock, it happens in finite. Now, when we put in back reaction, that story is going to change. Good. Any other discussion? This diagram is confusing and important. All right. So I'll just briefly flash up that I worked out the phase diagram. I don't know if that's the right word. For whatever reason, this hadn't been fully done in the 70s, so I just like fully did it. So if you're ever like building a spherical shell and you want to know whether it's going to form a black hole, you can just open up my paper and find out where you are in the parameter space. But I think in the interest of time, I'm not gonna review this. I'm just gonna point out that it depends on these three parameters. You pick the total mass, the total charge, and then also the material energy of the shell. So you can think about the choice of this as whether your shell is unbound or bound. So if you had small m, that would mean that you can reach infinity and you'd have finite kinetic energy at infinity, which is the difference between big M and little m. So that's the unbound shell. And if m is larger than big M, that's like a bound object, and like neutron stars that actually form black holes and so on. In our universe, this is actually greater than capital M. Those are slightly bound. So the closest astrophysics one is sort of sitting around here. But that's more of an advertisement. I don't think we need these details to make the point. So this is the generic picture. Let's forget about hitting the singularity. Let's focus on the black hole formation regime. So what you get is an event horizon, and the shell ends up at finite size, so macroscopic. There's no curvature singularity. Okay, so within spherical Einstein-Maxwell theory, there's no like infinite density at the center, all these things that get said about black holes. There's no time-like singularity, there's nothing. There's just matter that's approaching this Cauchy horizon at finite size. So that's an important point. Yeah.
Could you repeat why you have these three parameters, little m, big M?
So
like Q is clear.
Yeah.
But is there a limit when you basically take the shell away that it has to be flat space-time all around?
Yeah, capital M goes to zero.
What's big M in that case?
Zero.
Also, capital M is not independent of little m.
No, you can choose them independently. I mean, capital M has to be positive. There's a positive mass theorem. Little m could be anything. If you have m equals 0, you secretly have a null shell. Little m equals 0. It's like all kinetic energy, if you want to think of it that way. No rest energy. But those three parameters are just what you have in spherical collapse with an electrovacuum exterior and a flat interior. All right. So yeah, no singularities in this framework anywhere, ever. Now, if you read Wald's GR textbook from 1984, 3, something like that, or a variety of other sources back then, people said this Cauchy horizon is probably going to turn into a singularity. That's actually not true in classical GR. The mathematicians did some really heroic work and actually proved for us that the Cauchy horizon stays really just quite fine. But of course, what happens at the Cauchy horizon, as I emphasized, depends on everything that happens in the future. So this diagram is valid for a single fixed space-time. There's no back reaction from quanta. But in the real world, there's Hawking radiation. There's Hawking radiation goes out, and there's negative energy Hawking radiation that goes in. That's a firm prediction of semi-classical analysis. And so all that Hawking radiation from the whole future is actually going in, and it's going to interact with the shell. And so what happens to this Cauchy horizon, when you include perturbations beyond the 1970s GR story, really depends on back reaction from Hawking radiation. So I've never seen anyone make this point before. I'm tempted to like put my name next to the simple idea. It's kind of obvious, I think, but I haven't seen people talk about it. So you really do need to try. Now, what I tried is very simplistic, but in the last 10-15 minutes, I'll take you through how it works. So if you take that Reisner-Nordström space-time, and you have the mass m, which is a constant in the Reisner-Nordström space-time, and you just allow it to be a function of this Eddington-Finkelstein V, what you get turns out to have a very understandable stress energy tensor. It takes this form. If L is an ingoing null direction, the stress energy tensor is just proportional to L tensor L. So it's ingoing energy. And if you compute this thing, an expected value of stress tensor for Hawking radiation, you also find an ingoing energy component, and it's negative energy. So the Weijers space-time, as pointed out by Hiscock in 1981, is a very, very natural way to take into account back reaction from Hawking radiation in a classical way. Now, it doesn't give you everything, of course. It's certainly at best mean field. There's, and even there is going to well approximate the expected value of the stress energy tensor in Hawking's calculation. Well, it doesn't get all the components, but it gets the important one. It gets the negative energy ingoing flux. And that's the one that blows up at this Cauchy horizon that we have to worry about anyway. So this is how it works. So you literally, to model Hawking radiation, you just take your calculation you did in Reisner-Nordström, and now you allow M be a function of B. So I just picked some reasonable M equals M of B toy model that just shows it kind of decreasing. I'll give you an example. This is now the spatial picture. Maybe this clarifies some of what was being asked about Reisner-Nordström. So the picture is there's still a shell. Its interior is flat. It's by assumption. And now instead of the exterior being Reisner-Nordström, we assume it's a slowly changing mass of Reisner-Nordström called the Weijers space-time. And so then I drew these little squiggles that represent ingoing negative energy Hawking radiation that interacts with the shell, right? No singularity, interacts with the shell in this model just according to how Einstein's equation dictate the energetics. Now, if you want to make this palatable and faithfully, more faithfully represent Hawking radiation, you also have this outgoing region. Let's not worry about that in the interest of time. It doesn't affect the dynamics of the shell. It's just sort of there to make a complete model. Hiscock did that as well. The point I want to make is that this R plus, which was previously an event horizon at some fixed value, in this back-reacted model, this now has an evolving value. And it's interpreted as an apparent horizon that locally looks like an event horizon based on the behavior of light. The outgoing light doesn't increase in radius at this radius. And it evolves very slowly over the whole evaporation. And we just redo our solution of Einstein's equations. We now get a new trajectory for the shell. And I'll show you what I found. So the equations are very simple. This is just a simple consequence of Einstein's equation. Still the same parameters, except now they depend on time. So we had big Q, big M, and little m, right? So big Q is still constant. That's just what I'm interested in, right? This black hole has constant charge, but it's losing mass to Hawking radiation. Big M then depends on time in a way I prescribe, and then little m is just no longer constant in this context. It has this evolution equation. So, in hindsight, I don't know why I was so stressed out, but I was like killing myself trying to finish this paper. I was like, why has no one ever done this before? This should be done already. And I did the whole thing in 2 weeks. And this factor here gave me a huge amount of gray hair. I don't know. I don't see them yet, but they're coming. Because that thing in the denominator is going to zero rapidly. And that's this blue shift instability. And it's just there. I expected this to say little m prime equals big M prime. Right? Remember, little m is like the mass of the shell. And big M is the mass of the spacetime. So big M prime is the rate at which mass is being deposited on the shell. Right? I really expected just to have little m prime equal to that rate. The shell just picks up mass at that rate. But this is the difference between a shell and a particle. For a particle in special relativity, things work out because it has one tensor index, but this somehow has two, and this extra, it's really there. And it's going to infinity, and it complicates the analysis.
Can you see again where the second equation came from?
So it's all just coming from conservation of stress energy in this construction where you glue the Weijers space-time to flat space-time at some time variable radius. So M is a parameter in the stress energy tensor. So the stress energy tensor.
Is there some statement that this ingoing flux is getting absorbed by the shell or something, or passing through, or what?
One is tempted to make the state absorb, definitely not passing through because the interior is flat.
But you're being, it's all getting absorbed, or what's the?
That's the closest statement that I would make.
But-
Mathematically, yeah, I mean, I'm
But is
glad
there,
this stuff.
there's some freedom there? Is there some freedom like?
Not in this model, there should be in a better model, but in this model, the assumption is it's flat. And it's biject. So now the energetics, and you literally solve del mu, T mu nu equals 0 distributionally. And that tells you everything. There's also the assumption that the stress energy of this thing, T mu nu, this is going to look like some m over 4 pi. It's just a name for the component, but this has to be proportional. And there's some delta function as well. So this is the assumption that it's pressure free, it's pressureless. So that's where m comes in, and the conservation of stress energy just dictates. So yeah, I think it's all being absorbed, is the way to say it.
So that's the assumption that's flat inside.
Yeah. Okay, and then the top one is fine once you understand the bottom. But the top one is the same as in GR, where the m is constant. So now it just changes. So the implications of the bottom one with this blowing up factor on the right took me not long in hindsight, but longer than I would like to realize. It's actually telling you that this m parameter is evolving to 0 in finite time. This negative energy is coming in, the shell's absorbing it, it's taking away its mass. And it hits 0 in finite time. And when I first saw that, I kind of panicked, but then I realized, no, that's okay. Things can go to 0 as long as you also find that the energy is finite. And that's just the conversion. It's like an ultra-relativistic limit. It's like the conversion of a time-like trajectory into a null one. So this model predicts that the shell actually becomes null at some moment in time. There's nothing wrong with that. I found it surprising, and so I'll emphasize it. But the very interesting thing is it's always outgoing. So putting in this back reaction with this model of how it's absorbed by the shell collapses and then it ends up being null and outgoing. So it feels a little weird to say you're moving at the speed of light and moving outwards inside a black hole. That's kind of how black holes work because you can't get out of them. So if you're going to move at the speed of light, you're going to stay inside.
I mean, if the original shell was made out of physical charged particles, how is it absorbing and then becoming null? That's all.
Yeah, that's a big question. On the other hand, sort of baryon number violation is a basic property of black hole evaporation. So I would like to have a standard model process that could do this for me. I don't think there is one, but I don't think that's a reason to discard the model because the whole thing violates, standard model physics in the first place. My hope, is that by thinking about this, maybe we'll resolve the question, what kind of physics is needed. But that's a totally valid objection. Okay, so I'll just show you some numerics. You can derive this analytically that this happens, but it's nice to sort of put the whole thing together numerically. So solve those ODEs with some prescribed profiles. So I've taken my black hole mass here, my shell mass rather, to space-time mass to start at 1, and then just have some nice smooth evaporation to 1/2, or very nearly 1/2. So we become super extremal after this point where I declare by writing down the function that this last quantum was emitted, and then it just stays at that mass. And then you can solve for the radius of the shell given the choice of little m. And it looks like this. So you have to be a little careful in comparing these. I've got a log scale on the x-axis on the right, but not on the left. Okay. But it's necessary to show everything in one plot. Also the y-axis is log on the right, but not the left, but that's a different quantity. So the radius starts here at, 5, remember what it was. And it collapses very, very quickly. Okay, so notice this is 0.01 in these units, which doesn't even register. So already here on this plot, the thing has collapsed. And as I said it would, it actually collapses down to the inner horizon size. So the shell does not go to r equals 0, it goes to the size of r minus, and it sits there. And for the whole evaporation, so this whole period here is this evaporation period, it just tracks this. And you can see that the inner horizon radius is increasing as the mass of the black hole decreases, the inner horizon radius gets larger. So the shell is expanding its size, and then finally, at the moment when the space-time is no longer a black hole, the shell is free at last, it hangs out for quite some time before expanding to infinity. It's strictly null. At this point, I'm just solving the null field equations, but this thing is a black hole. It was very close to a black hole, so it's going to behave very much like one for a long time. So it lingers there and then it re-expands.
What's the time of the lingering?
Yeah. I'm a little worried the referee is going to make me work that out. It's going to be so annoying. I mean, it's kind of complicated. I mean, it could depend in detail on sort of how the last quantum was emitted, this discrete process I'm not modeling anyway. It also depends on exactly how close to R minus it gets, which depends on details of collapse. There are plots in the paper. I even have an analytic prediction for its deviation from R minus, and that's sort of initial conditions dependent. So there probably is a relationship between the initial conditions in my model and how long it lingers there, but I didn't bother to work it out. But I mean, the answer in practice is very long. All numbers in this problem are ridiculously large or small. Just to get to near extremal, you need many universe lifetimes. It's a theory problem. Okay, just to have pictures as well. Here it is in pictures. First thing that happens is the time-like shell collapses. And during evaporation, it's basically locked at the inner horizon. It's become null. And then when the horizon goes away, it just comes back. People don't like Penrose diagrams in this room, so I don't need to show that here's the version of the Penrose diagram. I want to emphasize it, but again, you always start at this point on the Penrose diagram. And shell reaches an inner radius, then it becomes null and comes back out. So this region is representing the whole evaporation. One thing that is of note is there's a null version of this story. And I could have started with this and I wouldn't have needed to do any calculations. So you might think that if you had the collapsing matter be speed of light ingoing in the first place, that it would just keep going. But it's actually been known since the 90s that's not what happens. It's a little subtle why, but in my model, I just derived it as a limit of time-like behavior. But the null shell is quite nice because it just bounces at arm-in and then re-expands. It's totally analytic. I don't need any of these numerical simulations that are annoying. You literally just take flat space-time and Reiser-Nordstrom and Weije, and you glue them together at certain regions. And that is the fully self-consistent model, exact solution of GR that, subject to the validity of these approximations, does represent this evaporation past extremality. So I've got a few more minutes, and my plan for the few more minutes is to flash up some of the limitations that have already been discussed, but just to give you an idea of the things I worried about and still worry about, and then talk about maybe some of the implications. So as discussed extensively, there are arguments that the semi-classical approximation breaks down in this regime, and so the prediction of emission of this last quantum is wrong. I want to learn more about those arguments. You might wonder that the thin shell model is too idealized. All this stuff I'm telling you about collapse, maybe you're thinking, this sounds weird, why would this be right? It's thin shell. Well, the thin shell is pretty well established, and the reason is, it's pressureless. So there's nothing holding this shell up. So like if I say it bounces, it's not because I put like bouncy material in the shell. It bounces because of the gravitational and electromagnetic forces acting on it. So I don't think, the story's gonna change at all if you do a star or something. Spherical symmetry you might worry about. I don't know. I'm not too worried, but one statement is that I really don't think you're going to see time-like singularities outside of spherical similarities, symmetry. I mean, that would mean time travel, and sort of even I won't allow time travel. So I'm fully expecting this bounce to be totally generic. I've been begging all my numerical friends to try to study the axisymmetric problem. They assure me they know it's interesting, but it's very hard. And then is this Weije model too simple? This is a real worry. I mean, this conversion to null at a finite time, that very well could be an artifact of the model. Maybe if you knew how negative energy Hawking quanta interacted with actual shells, you'd find something different. So that I would like to fix somehow someday. But energetically, the Vijay model has everything you could possibly want. It has the negative energy flux in the region you expect it to be from the semi-classical calculation, and it imposes conservation of energy at a macroscopic level. One implication I'd like to mention at the end is information issues. So I'm sure everyone's heard of the information paradox or puzzle. People think of it these days, but the basic idea is that, when a black hole radiates, it sure looks like a thermal state, which is a mixed state. And if the black hole is totally gone, it seems that you got a mixed state from a pure state, which should not be allowed by unitary evolution. I just want to point out that, if we accept the validity of this scenario, it's a really interesting way to study information flow in black holes. And the reason is because there's no singularity. You see diagrams of black hole evaporation, there's always a singularity. And people argue over what's supposed to happen. And at some point, someone says, well, we don't know because we need quantum gravity at the singular. Okay, for studying information flow in this scenario, where the black hole evaporates and then stops, you do not need quantum gravity. You certainly don't need strong quantum gravity. You might need some other corrections or something, but space-time curvature is globally small. So that's notable. And, in particular, you could imagine actually following the flow of information. You could imagine the shell went in, it got bathed by these Hawking quanta, it picked up correlations with the outgoing Hawking quanta, and then it came back out. And your state is not only pure in theory, it's pure in practice, because you've got the purification right there in the shell. So I just think this is interesting. If anyone's thought about page time issues, the cool thing here is you can tune whether there's a page time or not, just by picking how initially non-extremal the black hole is. These are some things I'd like to do. Definitely like to improve the model of interaction between radiation and shell. I don't know how to do that. But maybe that's what you did, found a different answer. I've already mentioned rotating matter. I'd really like to see something go wrong within the Hawking assumptions. That would convince me. And ADS might be interesting. I'm an ADS ignoramus. All right, so I'm going to leave with one takeaway in a talk that I think was speculative, more than I'm used to, but potentially very interesting. And the takeaway is that it's not a big deal to go super extreme. And if you look at what people say in person, what's written in literature, there's this kind of palpable discomfort with that idea, like some catastrophic thing to destroy a horizon. The AI comes up with the big red, jagged, super extremal object. I mean, I really think that's wrong. It's really not that scary. The space-time is very, very similar before and after this event. There is no time-like singularity suddenly visible and ruining everything. There's just matter inside that black hole, just in the model I've written down. And so when it's not a black hole, the matter just comes out. So my takeaway is it's not that scary, and maybe it's even a little bit exciting. Thank you.
So you're regarding the pure Schwarzschild collapse is kind of a special, this would obviously not go work there, but you're just viewing that as like.
Yeah. I think it's non-generic. Yeah, I can't prove it, but I'm trying. I mean, you have to either argue that, of course, the whole Kerr-Newman family that represents black holes, every point in that family has a time-like singularity, except for Schwarzschild. So it's a little strange to think that Schwarzschild is the generic case, but that has been the standard view, with the idea that the Cauchy horizon will somehow magically turn into a space-like singularity, but it doesn't. So I think it's time to give up that view. Go to the other one. And yeah, that's, I hope, a real contribution, even if all this quantum stuff is wrong. That's just a statement about classical geo.
All right, let's thank Sam again.